Welcome to the first lesson of the course GEO1004, 3D Modeling of the Built Environment. This is a course of the Master of Science in Geomatics at the Delft University of Technology. If you're formally following the course, make sure you have already read the About page on the course website, which is also linked below. Now let's move on to the topic of this lesson, which is a sort of introduction covering basic concepts that will be useful to better understand the rest of the course. In this introductory lesson, we will cover three topics. In the context of geographic information, what is a 3D model and how it is made? How 3D modeling is related to some common spatial concepts? And the difference between a data model and a data structure. Let's start by discussing what is a 3D model and how it is made. In the context of geographic information, 3D models are digital representations of real-world objects, including buildings, terrain, and infrastructure. These representations can take very different forms. They can also be quite complex, containing a mixture of geometric, topological, and semantic information. Let's look at some typical examples. 3D city models are representations of large areas, usually composed of 2D surfaces that have semantic information attached to them. The focus is on modeling buildings, but other features that are present in an area are also covered, like terrain and water bodies, as well as more urban features such as roads and city furniture. Building information models, or BIM models in short, are similar to 3D city models, but they cover only one building site, which can be a building or an infrastructure project. Unlike 3D city models, the elements in a BIM model are mostly 3D volumetric objects that correspond to physical objects that have to be built, such as beams, concrete slabs, or windows. Point clouds are a different type of 3D representation that consists only of points, which are sometimes classified or processed in some other way. Unlike the other two representations, they capture everything that is visible in a given area, but they do not have much structure or semantics. The three examples we covered are all very different. All of these representations consist of elements of different dimensionality. 0D elements in a point cloud, 2D elements in a 3D city model, and 3D elements in a BIM model. The different representations can also have a lot of structure or very little, and a lot of semantics or almost none. But the important thing is that they are all representations of geographic information in 3 dimensions, and each of them is suited for particular applications. They are also created using broadly similar processes, which start from the acquisition of simple data, such as individual measurements or data from a variety of sensors. The raw data is then iteratively processed to obtain more new data, which is semantically richer and more complex. This brings us to the second topic of the lesson, which is about some important spatial concepts that are useful for the rest of the course. The first of these concepts is the Geoinformation chain, which is just a formal way to refer to the same general process that we just mentioned for the creation of a 3D city model. The idea is that geoinformation is usually created and used in a specific order, starting from the acquisition of raw data, moving through several processing steps, up to the point where we have the data ready for a particular application. In this process, the output data for one step is the input data for the next. The important thing to consider here is that in this course, we will be covering many kinds of representations, but they don't all fall in the same place in the geoinformation chain. Some will be closer to the raw acquired data, and some are only obtained after a lot of processing. But all of them have strengths and weaknesses and are useful for particular types of applications. The next spatial concept refers to 2 different ways of conceptualizing the world: objects and fields. In the objects view, space is empty and is populated by discrete objects, and so we can create 3D models of these objects. In the fields view, space is filled with certain attributes such as elevation or temperature. We can then create 3D models that tell us the approximate value of these attributes at a given location. The next spatial concepts are 3 kinds of geometric definitions that we will be using. In Euclidean geometry, we start from the basic geometric axioms, such as defining a line by saying that it is the line passing through 2 points. In Cartesian geometry, we consider coordinates, and so we can define the 2 points based on their x and y coordinates, or we can define a line through an equation based on its slope and its y-intercept. Finally, in points at geometry, we can define the line as a set of points fulfilling a certain condition, such as that the line is a linear combination of the 2 points. Moving on to the final concept, we will also be relying on definitions based on graphs and algebraic topology. You might be more familiar with graphs, which we can use, for example, to define a polygon based on a few vertices connected by directed edges in a loop. Algebraic topology uses higher dimensional elements than just 0D vertices and 1D edges. For instance, we can represent the same polygon using a set of 2D triangles that are known as 2 simplices. Finally, let's finish the lesson by clarifying the difference between data models and data structures. So far, we have only been talking about representations in general, but there are actually different kinds of representations. Usually, when we model reality, we start by creating a high-level model that is close to the way we conceptualize the world. We can define some abstract objects with some attributes, such as a house composed of a roof and walls. This is a data model. Then, starting from a data model, we move on to a low-level structure that is close to something we can implement in a computer. Rather than real-world objects, we can then define things in terms of simple structures, such as lists, tuples, or sets. This is a data structure. Now, considering that this is the first lesson, you might be wondering what to do next. I could suggest you to first read the handout, then try to answer the questions at the end of it. If you have any doubts about the material or the questions, just tell us in person in the lab or post something in the discussion forum online. And finally, spend a bit of time to follow some of the sources we list in the notes at the end of the handout. For this lesson, I think the most interesting one is the 1992 paper by Andrew Frank. Can you find what is still true and what is out of date?